So, hi everyone, and today we welcome Mazi Jalaal from the University of Amsterdam. So, Mazi is originally from a wonderful country, which is Iran, and then he moved to Canada, where he did his PhD with Neil Balmfort, and then moved to the Netherlands first time to do a postdoc with Detlef Loze for a couple of years. Then he went to the University of Cambridge in the group of Ray Goldstein, where we met, and he worked on squeezing cells in order to make them emit light. And now he has his position as an assistant professor at the University of Amsterdam, and he will present us his work. Thank you.
Thanks so much, Helen. Thanks so much for having me. It's a great honor to be here. Most of you probably don't know me, but this institute has been very influential during my graduate study and until now and as today. Since my master, I started working with Jerry's, and since then I'm following everything in this institute from granular materials to all that capillarity, and you might see some effects actually in my presentation. Again, since most of you don't know me, I thought I'd take half a minute to say what my labs actually looks like now at University of Amsterdam. So my background is actually very mixed between complex fluids and biophysics, and that's also now shows up in the lab. So half of the group are doing yield stress fluids, which I will talk about it, and active matter, physical chemical driven hydrodynamic system, and the other half doing completely irrelevant things on microsomas and non-motile also microorganisms, and a little bit now we are moving to biophysics of cells even in our group. Sometimes, in some cases, these two universes meet each other. So we start looking at biophysics applications or biophysics problem from a complex fluids perspective. Well, today I'm not going to talk about anything living. As the title of the talk says, it's about yield stress fluids under surface tension. So this is a field that I start calling it plastocapillarity. So if you're not familiar, what I mean is that if you look at dictionaries, what plasticity means, I'm sure a lot of you know about it. It's basically, this is a definition from Cambridge Dictionary about the quality of soft materials being deformed, and typically it's an irreversible deformation, i.e. plasticity, and capillarity, that most of dictionary actually define it in the wrong way. So it's basically the action of surface tension that drives the fluid, and many of you are working on it on this topic. So basically what I mean by plastocapillarity is the flow, is the phenomenal flow of yield stress material due to surface tensions. So why this is important? So to look at it, you should think about length scales, because size actually quite matters. So the way to look at it, the easiest way is that to look at the capillarity length scale, surface tension sigma over rho g, density and gravity, the root square of that. For water, most of liquids, this is order of a millimeter, right? So there is a large body of work on flow of viscoplastic or yield stress materials that are in a very, very large scale, order of meter or kilometers, and that's mostly related to geophysical applications. So here is an example of mudslides in California. So you can model such phenomena as, for instance, with a viscoplastic or yield stress material. You step back and you look at it as a continuum mechanics problem, and you say my mud has some yield stress in it. It's a plastic, viscoplastic materials and flows. So there's a very nice review by Christophe Ancet on that. But there, the scales are so big that you don't care about surface tensions, because it's basically all gravity driven. However, if you go to much smaller scales, to the scales of droplets, for instance, then your length scale is comparison with the capillarity length scale. Therefore, surface tension is important. And if your material is yield stress material, that's where plastocapillarity becomes important. And that's the regime you're interested in. So in 2-3 slides, I'm going to go through and tell you what has been done in the field. So I try to do a very quick review. So there are multiple aspects that people work on it. One of is around droplets, so droplets of yield stress fluids. This is from the lab of Wolfgang Bertolo in Liverpool. So what he does is the simplest experiment you can imagine. You get a needle, you start ejecting droplets of yield stress material. So imagine you have hair gel or toothpaste, and you want to make a droplet out of it. If it's a Newtonian droplet, you can get almost a spherical one, so surface tension wants to be minimized, right? So you get a sphere. But if you add yield stress to it, at some point you get more elongated droplets. So this is the moment that droplet wants to be retracted by surface tension, but yield stress resists, and it doesn't go to the spherical. So you get elongated. The larger the yield stress, the more elongated it is. There are some nice work from group of Bertolo, but some others. There are a class of work also on droplets that are mostly inertia driven. So yield stress and plasticity and elasticity compete with inertia. So I listed some of them there, but they're quite different because surface tension doesn't play the role there in most of those work. So we work on impact of droplet formation and impact of droplets. I'm not going to talk about it, but I thought it would be interesting to show just an example that what you can do with such droplets. So what we found out is that if you get these droplets, the elongated one, and you let them pass through a water-air interface, because this is a plastic medium, as it passes through the interface, it can get deformed, and then plasticity dominates and it keeps the shape. So we found an experimental method as simple as that could be used as long as you have surface tension and plasticity together to tune droplets of different shapes. So you can tune this shape and it's completely permanent afterwards by just changing either the plasticity, yield stress, or the impact velocity. What happened to be very surprising for us was that if you increase the speed rather large, you can start encapsulating air. Maybe you don't see it, but there's a tiny bubble inside the droplet. And that's a very, very niche regime that if you control your parameter nicely, you can somehow sample the gas on top while you droplet. And funny enough, this looks like a life jacket. So the bubble buoyancy wants to keep the droplet up, and the material itself is a little bit dense, so the droplet stays there for minutes, in fact. So I'm not going to talk about it, but if you're interested, you can have a look at that later. So that's about droplets, which I will come back to it later. And there's another category of bubbles. I took this work from the group of Ian Freegard at UBC, which has extensively worked on bubble dynamics in viscoplastic fluids. This is a static picture, so this is not this is a steady state. So you can look at hair gel or mayo, and you can always see these bubbles that are static there. The reason that you can get this different non-universal or non-unique shape of bubbles is that, again, the yield stress. Surface tension wants to keep the bubble spherical, but the yield stress doesn't allow it. There are some really nice set of work on bubbles, and more recently on the cavitation of bubbles related to the cavitation dynamic in soft tissues. But we also look at this using basilisk, in fact. And what we did the problem of bubble bursting, which people in this institute should know very well about it. So it's a bubble that is sitting on the top of the liquids. There's a little hole there. This is time0, and we let it burst, basically. So for a Newtonian fluid, is very well known, and there's a lot of complexity already in a Newtonian case. We thought, let's make it more complicated, and then we make this liquid here actually viscoplastic. So we added yield stress, and there's no gravity here, so it's a pure plastocapillarity problem. Surface tension wants to minimize the surface, collapse the bubble, and yield stress in the bulk is resisting it. So the color, you can look at it as a deformation. You get these Worthington jets and the bubble and everything. What is more interesting that how stress distributes in the surface, in the liquid, in the bulk, and as a result, you get a uniform interface in the end. So that's the solution to it. You change the yield stress or the plastocapillary number, you get different regimes. You can think about it in the limit that everything is plastic, this won't collapse. And we found out there's a lot of application in geophysics for the volcanoes, for instance, or mud volcanoes, when the mud as a viscoplastic materials actually collapse bubbles. These are the gas released underneath. Okay, so the applications that I'm going to talk actually mostly today is related to the application of coating. There are many methods of coating. In fact, one of them is droplet based. So you have a system like an inkjet printer system. You generate droplets that are sitting next to each other one by one, and you coat a line or print something, or you can do it in 3 dimensions and do 3D printing. The other coating methods is dip coating, for instance, that you get a fiber or you get a plate, you dip it into your materials, and you take it out, and what remains is the very thin film of the liquid. These are classical fluid mechanics problem. If you open classical hydrodynamics books, there is solutions for this in the Newtonian limit, in fact. But what I'm interested is not exactly this, but 3D printing applications. If you look at what we can now these days 3D print, basically by what is available on the shelf, you can print materials like plastics, clays, and more recently foods even. And what they actually commonly have in feature is plasticity, because you need yield stress, you need some plastic property to keep your material in 3 dimensions, in fact. And it's either thermoplastic after the solidifications, or clays also after they age, or the food, in the case of like ketchup or mayo, they come with this soft viscoplastic behavior anyway. So if you don't know how 3D printers work, that is what I always show. That's a whole mechanism of it. So what you need is a pressure source, and a nozzle, and a viscoplastic material that can sustain a 3D shape to some extent. And you need a substrate that is hard or soft, so you can print on it. So in a reality, what operators do is basically this nozzle is on a robotic arm. You program the robotic arm and you go and 3D print things. So here's an example in our lab with a very soft material with a yield stress of 100 Pascal. And what I'm printing is letters. I was giving this talk to Journal of Non-Newtonian Fluid Mechanics, so I'm going to print J, N, N, F, M. And what happens is the robot goes, puts the lines on the surface, and this keep doing this depending on the on the program you give it. So you start printing a second layer, and you start printing multiple layer. And if your material can hold the weight, you can go as big as you can go, basically. Okay, but the key is you're in a smaller scale, so surface tension is important. At the same time, the material has this elastoplastic properties. Okay, so motivated by that, I'm going to talk mostly, I won't get talk about this, but I will talk about 2 problems, how droplets spread on the surface, how these filaments in 3D printed spread on the surface. So surface tension will spread it, but they are also plastic. So what's the mechanism there? And can we come up with the mechanism based on the findings there to control this spreading on the surface? And that relates to the problem of solidification, which I come to here. Okay, so the simplest problem is this. Imagine you have a surface. Let's say it's pre-wetted, so let's get rid of all the complexity of the contact line for now. And you put a droplet on it, and that's your T0. If this was a Newtonian droplet, this will spread at T infinity. This must be flat surface, right? So surface tension let it spread, or gravity, but there's nothing to stop the droplet, so this will spread for us. But if this is a viscoplastic case, it will be different. But before going there fast, I just want to mention that even this problem in a Newtonian limit has a lot of interesting features. In particular, what happens in this regime when the contact line merge this interface goes through some very interesting topological changes. I'm not going to talk about it, but long story short, that you get some sort of undulations on the interface. And what we found out that it heavily depends on the capillary number, how fast the moving front is moving, which results to a new type of singularity we found out at the capillary point 3, which we can also get from theory. So if you're interested, we can talk about it later today. So we wanna look at this problem about viscoplastic fluids. I said it already a lot, but just in case you don't know what it is. What I mean by viscoplastic fluids is I'm referring to this very large class of materials that can have different origin in a molecular scale, for instance. So they can be Brownian or non-Brownian suspensions, or they can be foams, for instance, or they can be emulsions even. So that doesn't matter because I'm going to look at the continuum mechanics, but they have something in the smaller scales that form a network that if you don't put the stress on them, they're going to hold the stress on. But if you put shear on them and this shear is above a critical stress, you're going to, naively speaking, break this network and let it flow. Okay, so you go from solid to liquid transition if you want. Mathematically speaking, the easiest way maybe to look at it is to look at this curve, the so-called flow curve. So this is shear rate and that's shear stress. For a Newtonian fluid, this is going to be a straight line from the origin, and the slope of the line is viscosity. But for a yield stress fluid, you have this offset in the stress, and that's your yield stress. And the simplest case of viscoplastic fluid is the Bingham fluid, where viscosity is linear, but most of the time, viscosity in reality is also non-linear. You have shear thinning behavior, for instance. Okay, in the tensorial form, you can write it like this. There's no deformation rate if a stress is below the yield stress. If stress is above the yield stress, then you get some deformation. All right. So this was the Newtonian problem for so what that brings is that if this fluid was viscoplastic, at T infinity you get to the final shape. And this heavily relates to the 3D printing problem I told you, because you can think of this as a filament width or a droplet that you deposit, and that relates directly to the resolution of your 3D printer. So it's very important, even from the application point of view, that to see when it spreads, how does it spread, and how big is this final shape. That is dictated by the surface tension which wants to spread it, and yield stress which stops it. So it stops when the stress is below the yield stress. Okay, so I'm going to answer to those two questions. So you can do a lot of mathematics, and I don't show it, but I will come back to it. But the easiest way to answer this question, that what is this final radius, is via scaling law. So imagine you have a droplet with a given volume V. In the end, you have HF, final height, and RF squared. So imagine this is a spherical cap. So you can correlate your volume with that. And at the same time, you can introduce a characteristic length scale L, which is as if this volume was a sphere, L was the radius of that sphere. Okay, so I'm going to look at RF at T infinity when the droplets spread. So you can do that in the limit of pure plastocapillarity by balancing the capillary forces and yield stress forces at the moment droplet stops spreading, right? So what is that? So capillary force comes from curvature, from surface tension. Those are the characteristic length scales for that. And yield surface, we only assume that the yield stress at the bottom, at the wall, that's where the stress is maximized. So if that is equal to yield stress, that's the moment that droplet stops. So all you need is to actually balance these two forces. You have a given volume, so you can, for instance, cancel off HF here, and you immediately get a scaling law like that. So RF is the final radius over the characteristic length scale L. So if you know the volume, you know L. Omega C is a coefficient in your scaling law. So if you don't know what that is, but then you get this weak dependency on non-dimensional number J, which I call the plastocapillary number, which is the ratio of the yield stress versus surface tension. Okay, so yield stress at surface tension of capillary pressure, in a sense. Okay, so and here it is. So we already got it. So the question is, what is omega C? So I could potentially give up at this point and say I fit to the experimental data and get omega C, but we spend more time on that to find it, and I come back to it in 2 slides. Just have a note that such balance have been used also previously in a couple of works that study droplets and bubbles in viscoplastic fluids. The other limit is that your droplet is very, very big. So there are also 3D printers who are in a very large scale. These are printers, for instance, that print concrete to 3D print houses, for instance. Or you can think again about the geophysical application. So you have an avalanche of snow, and your snow is viscoplastic. There, all you need is to balance gravitational forces with yield stress forces. That's the same thing, and that's just hydrostatic force. And there you get a different scaling for your final radius. And here you now get a different non-dimensional number B, which is the bone number, compressed gravity with surface tension. Okay. If you do the simple algebra here, surface tension is not there. I just write it this way, so you get the plastocapillary number everywhere. The cool thing, or the easy things about gravity dominant domain is that equations are much simpler, because gravity works with the first order derivative of interface, and surface tension has curvature on a higher order, so you can get omega G much easier, and I'll get back to it. So we were keen that what is omega C and what is omega G, for instance. So we start looking at lubrication theory, but you need to modify lubrication theory because of yield stress. So this is shallow water limit I'm going to talk about. So the assumptions we make there is that my droplet or my flow is very shallow, meaning that the length scale in this direction, if it's order L, the height is order epsilon L, epsilon being a small part. Okay, so you start from Navier-Stokes, you change the stress tensor because you now have plastic deformation in it. I'll show you in a second. If this was Newtonian, you had the parabolic velocity field, and you again, coming from Navier-Stokes, you go and you do the height averaging as it's known, and I've cited a lot of paper here, and you get these differential equations, which is h being the interface height. The derivative of that respect to time, you have on the right side the pressure gradient and this h cubed, so you can think about it like a diffusion-like equations, okay? And this all is the derivative. I write it down in a axisymmetric coordinate. That's why you have 1 over r there. So pressure has two sources. One is the gravitational term, which, as you can see, is linear with h, and b is d bone number. And this term comes from curvature and has a higher order terms. That's what I meant, that the mathematically, when you have surface tension because of curvature, equations get a little bit more complicated. Okay? And so this equation, it has been known for Newtonian fluids for a very long time. What happens that if you have a yield stress fluid, at some point, a stress inside your film becomes equal to the yield stress, meaning that below that stress, above that stress, you can yield the fluid, so you can get deformation. So that's how the flow looks like. But above that, the stress is below the yield stress. Therefore, you do not get deformation, and that's where you get this plug-like or pseudo-plug region on top. So similar things happens also in granular materials. And if you start from this and redo the calculations, your thin film equation is going to change. So I have the pretty much same thing, but instead of h cubed, I have 3h. I have y squared 3h minus y. So what does that mean? Y is where this location of yield surface is, and that looks like this. So this is, forget about max. So it's h minus plastocapillar number over the pressure of grade. So if y goes all the way down, that means that everything is plugged up, so nothing moves. So ht is 0. If y goes to h, this becomes h cubed, and I retrieve the Newtonian thin-film equation. Okay, so I can solve these equations potentially, which we did with finite difference method. And here's an example of solutions for a given plastocapillar number and bone number and the thickness of the pre-wetted film. Okay, so this is the initial conditions. I let it flow, and over time it slows down, but it stops at what I'm showing at the with the golden line. So the golden line is where a stress inside the droplet everywhere is below the yield stress, so it doesn't move anymore. So plasticity dominates. If you're curious that how this y yield surface looks like, so for this snapshot of blue line, this looks like this. So at the center is 0, and as it goes to the edge of the droplet, it goes back. So it has quite a nonlinear form too. But we also find out, and it happens to be very important, is what happens at the edge of the droplet. So this gets very technical in terms of mathematics, but it happened to be very important, and I'll tell you why in a slide. So if you zoom in the position that the droplet is merging to the thin film, you start getting these undulations. And these undulations are not unique for non-Newtonian viscoplastic fluids. They also happen in the Newtonian fluids, which we later find the experimental evidence for it too. But for the yield stress fluids, they have a very different origin, and they also behave, again, mathematically very differently and much harder. And you can see it even in the final shape. And why it's important? Because if you want to get the final shape, if I go back to the equations that I have, I don't need to solve these equations in the full form of it. All I need is to go to y equal to 0, the limit that everything stops. And that's where this term goes to 0. So all I need is actually to solve this. But then I have a boundary value problem. So I need my boundary condition at the center of droplet, which is fairly easy, but also at the edge of the droplet. And so I have to know what's happening at these undulations to know the boundary conditions there. And that's why it took us a long time to understand that. So this equation is maybe looks simpler, but it's not that actually innocent. So if you open it up, it looks like that. So now my problem is a boundary value differential equation. So that's my differential equations, the third order, and I have this sine function on the right, because when the interface goes, when these undulations happens, depends if you're above h infinity or below it, that changes the sign of the pressure in your system. So you solve it now with again with finite difference in the shooting method, and you get a final shape. So this is not dynamic, this is T infinity. So one of these lines, I forgot which one, is coming from finite difference solution, one of them from this solution. No, there's no gravity, so B is 0. Yeah. You can add the gravity rather easily, but I will show some results with gravity. Yes, exactly. So if you have gravity, you get this pancake form, in fact, exactly. But you get this final shape exactly because, so another thing is, maybe I can say it, is that this curvature is rather high, but yield stress can sustain curvature. So that's the main difference. So maybe the last mathematical detail I will talk today is that I can look at the derivatives here, and just to show you that how the dynamics here looks like. And you see this sawtooth form of function at this edge and these undulations that I told you. And that's because this is as if it gave us some hint that this is as if I have I can maybe model these undulations or assume that there are some sort of parabola, in a sense, to understand what happens in this point at the edge of the drop. Okay, so I don't show the detail, but we need to do two things. First of all, we have to show that the proof of existence of a point here that where these undulations end. Because in the Newtonian fluids, you can write the equations, and these undulations go forever. Amplitude exponentially decays, but it goes forever. But for viscoplastic fluids, there is a point that these undulations, not only the amplitude, but wavelength also goes down, and that gives you geometric series, and there's a point that these undulations finish. And that's where we find the boundary condition, then you can do this. Okay, so all I said can basically go to this equation. So why we did this, if you remember, I had this scaling law, but I didn't know what is omega. So now you can run this asymptotic solution just for the final shape for different plastocapillary number and bone number to include how much surface tension, how much gravity you have, and get this omega. So you can run, I don't know, 1 million of these numerical solutions, and that's the results that you get. So now this is like a readout table for you. So if you know what is H infinity, what's the bone number, and what is the plastocapillary number in your system, in your 3D printing or whatever system, you can come here and put the numbers there and find your omega. So if you know your volume, you know what's the final radius. So we did this, we were very proud of it, and it was time to actually see if this is correct or not. Oh, maybe I show two limits. So what are those numbers? If you have pure surface tension, that numbers happen to be 1.75. So good news is order 1. And you have a gravitational term, or pure gravity in a geophysical problem, the number is 25 over 8 over 1 over 5. But this has been known, because again, equations are much simpler when is only gravity. So you could know this much easier way. All right, so time to do experiment. It's very simple. We get a nozzle, we inject our viscoplastic fluids out of it, we pre-wet the surface, and we look at it by camera. But the surface, there's a tiny technicality that also took us a long time to solve it. These materials, when you go to the lab, they kind of slip on the surface. So they have these polymeric blobs that when they go close to the surface, there's elastohydrodynamic theory that shows how. They deform, and the solvent remains underneath this polymer, so you get an apparent slip. So it's not Navier slip or something. This is as if you have a very solid thing that moves on top of another solid. So it's very important to get rid of that if you want to compare with theory. So we did that by treating the surface chemically. So we now know that there's an easy solution for that. So the materials we use are carbopol gel that you might have heard about them. These are basically hair gel. So if you buy commercial hair gel, it is carbopol gel. Many of the hand sanitizers that we used in the past 2 years are the same thing. Here are the rheology of them. So if you do oscillatory test to get G prime, G double prime, viscous and loss module or elastic module, what you get is at low stresses, the material looks like a linear weakly viscoelastic solid. So this is G prime, this is G double prime. So if you move it with a little bit of a stress, they just shake like a jelly. But if you put enough shear on them or enough stress on them, they start to yield, and the order of magnitude of G prime and G double prime, both of them drop significantly. So material remains viscoelastic, but is weakly viscoelastic. So this is known as a model material, because if you yield it, the viscoelastic behavior drops quite significantly. After that, you can look at the flow curve that I showed you before, and you get these nice curves that show nonlinear shear thinning viscosity too, and you can fit through it and characterize it. So this is Herschel-Buckley fluid, if you're familiar with it. And it's very easy to tune the rheological properties. You just change the polymer concentration. You get different yield stress, G prime, G double prime, etc. Okay? So this is how the experiments look like. Like I told you, it's very simple. You start injecting a liquid, and you stop it, and it relaxes after a while, and you get to the final shape. So what it looks like, this is the final shape for different yield stresses. So this is at a small yield stress. So it's very watery, but it still has some plasticity in it. It spreads a lot more. You increase the yield stress, it spreads less. It's not really rocket science. It's as if you have a stiffer material, surface tension is not strong enough to spread your droplet. And if it's very watery, surface tension is strong enough. But at some point when it becomes shallow, yield stress becomes dominant and stops the droplet from spreading. Okay, so it was time to compare with the theory, and we did it. So this is final radius of the droplet over the characteristic length scale, which is from volume, as a function of plastocapillary number. These are the theoretical prediction out of the asymptotic solutions that I showed you, and these are the experimental points. So good news was that these scaling laws that we got from -1/7 and -1/5, they seems to remain in the experiment. We could see them in the experiments too. The bad news was that the comparison wasn't really great. So our theory over-predicts, in a sense, our experimental results. And we were not sure what were exactly. We have a lot of ideas that why we get this offset, but it's very hard to prove which one is correct. For instance, if I want to say one of them, it's not clear what's the surface tension of these materials that we use. We use water as a reference, but you cannot use any of the common methods of surface tension measurements because they don't form a spherical droplets. So you can use tensiometer or things like that. So that's one problem, but there are a lot more that might cause this. But something that we thought we are not doing correctly was that my theory, if you remember, was in a shallow limit, and we thought maybe this is the effect of that. So these droplets are not particularly very shallow. So maybe if I don't do that and I solve the whole equations in a non-shallow limit, we can address that. So that's where we went to Basilis, Jerry's on that side, and we solved the full Navier-Stokes. Basically, all you need to do, so that's continuity equation, that's momentum balance. You need to play with tau here, and your stress tensor, and the way we do it, D as a deformation rate tensor. We do basically the same thing that I told you before. If a stress is below air yield stress, that should be 0, and above that, that must deform the fluid with a plastic viscosity and the contribution of yield stress. The trick is that to get this exact transition from yielding on yielding, you need to do some tricks. There are two different methods: augmented Lagrangian, or you do regularization of your Bingham model, and that's what we do. So I assume my solid state is a liquid with a very, very large viscosity. Okay, so in a non-dimensional form, that comes as a Ohnesorg number. That is a non-dimensional viscosity. So we solved this with Jerry's or Basilis, for instance, like the bubble collapse that I showed you in the beginning. And here are the solutions. So this is a droplet. Again, no gravity. So this is almost times 0. The color that I'm showing is the log 10 of the deformation rate, meaning that if it's black or dark, there's not much deformation, and if it is white, this is a lot of deformation. So here is curvature is maximized, so you get a lot of deformation, starts spreading. There are a couple of interesting things about the anatomy of the flow. One, at the center, you get this zone that looks like a static plug, so nothing moves, fluid doesn't move there. That's also a stagnation point. And you also get these zones too at the interface where it's a moving plug. So you also get a low deformation as move with the interface, basically. And important thing is that if you wait long enough, you get a shape that everything is black, meaning that nothing moves here. That's your final shape. So we can compare this with the map I showed you before. And here is the comparison. So red experiments, line theory, blue simulations. And simulations works very well when you compare with the theory, in fact. So it seems like the shallow assumption was not that bad in the end, but they still over-predict the experiment. So that hints us maybe we are measuring some of the property in our experiments, maybe not not accurately. So we ended up there. So you might ask what's happening here when everything doesn't compare with anything. So you should remember that these are very large plastocapillary number is when yield stress is with dominant. So you can think of if you want to deposit a droplet of toothpaste, it heavily depends how you do it. So it's memory dependent. So the method of deposition matters a lot. So the solution that you get in experiments, for instance, is not unique anymore. So that's what's happening there. How much time I have? Okay. So then I very quickly tell you, more recently by our experimental collaborators, we're moving to the system that is closer to 3D printer, and that's filament depositions. So I won't talk about it in detail, but it's the exact same problem in a sense. But instead of having axisymmetric system, I now hold my nozzle and move the surface and deposit a line on it, because that's how 3D printers in fact work. And then the problem is in principle the same. Droplets start spreading over time, so you can look at it as a pseudo time if you want. And the question is, what is that final shape? Because you want to know that when you do bioprinting of cells with gels in it, gels with cells in it. Okay, and I can maybe jump quickly. This is how the experimental setup look like, and this is the results. So you get a different scaling law, basically, different prefactor, different power law, but the comparison is what I call fair. But there's still some discrepancy that it's very also hard to get a larger value of J's. If you go very, very large, you get a constant radius, and that's a different regime. That's a pure plastic regime. So for this regime, this is how far we got. And you should remember there's no fitting parameter or anything in this. This comes directly from asymptotic solution of the governing equation. Okay, so we've done a lot of these things, and we got some insight how viscoplastic droplets basically behave. The question was, can we use this knowledge to control externally how much droplet spreads? So that gives us a hint that can we turn our droplet to a yield stress droplet on fly, basically. That's what I'm going to talk about briefly in a few slides. Okay, so that's the next question. So then we raise this question, can we make viscoplastic materials with heat by heating them? For that, we went to this type of polymer known as a tri-block copolymer known as pluronic. So it looks like this. It has two PEO, polyethylene oxide, on two sides and one PPO in the center. They have different hydrophobic, hydrophilic properties, these polymers. That's why they show very funny behavior. Long story short, if you solve them in liquid, they look like watery material, and you heat them up, they start forming micelles because of this hydrophilic, hydrophobic property. And these micelles start packing to each other, and you start forming a gel. And it's like magic. I mean, if you ever get the chance to see them, they're flowing, and if you tune the polymer concentration, you can hold it in your hand, and they suddenly become like a completely jelly material, in a sense. So first thing, we did a lot of rheology of these materials. We showed that there is a line. This is concentration of polymer, and that's the temperature. And if you pass this line, you go from completely Newtonian behavior to completely viscoplastic material with a significant yield stress, in fact. So we thought maybe we can use this actually to control the shape of droplets on the surface. If rheologists in the audience are interested, what we saw that at very large temperatures, your material stay viscoplastic, but you start getting some instability, which was a hint of shear banding and those things, which I'm not going to talk about. Okay, so experiments look like this. I'm going to flow these thermo-responsive materials on a heater, and I look from side, but we just don't do side imaging. We also look at it with the device or with technique called optical coherence tomography. So optical coherence tomography, in short, is an interferometry technique, but instead of using only one coherent light, like one single laser, you use the whole spectrum of white light. So the benefit that it gives you is that you can penetrate in depth of your liquid when you use this. If you ever go to eye doctor that put this device on your eyes to look at the back of your eyes, that's most likely optical coherence tomography. So it's being used in biomedical imaging, so we now are basically using it for some soft matter problems. So the way I use optical coherence tomography is that I want to get information from inside the droplet. So this now connects with the solidification problem that many of you are working on here. So the idea is that the liquid is Newtonian spreading. I heat it up, and can I see where it solidifies or become a viscoplastic materials, in fact. So we tweaked the method a little bit, so we went to somehow do some sort of micro-rheology with it. So what I've done is that in this voxel of measurements, I put Brownian particles in it, and these Brownian particles move because of thermal fluctuations. We don't see them, so they are much smaller than the resolution of my device, but I can see the local light interference because of the thermal fluctuation. So therefore, what you get is some sort of signal like that. So let me show you what happens. So what I'm going to compare is the same solutions. One at low temperature when it's Newtonian, so this particle can do thermal fluctuations, and one at high temperatures where this particle cannot do thermal fluctuation. If you look at the static pictures, they're exactly the same thing, but there's dynamical features in them. So here particles are doing thermal Brownian motion to give you this local interference, but here you only get noise. If you look carefully, there's some noise, but that's just noise. So you can do autocorrelation of the signal, and from there to see where you have Newtonian and when you have solid or viscoplastic. Okay. So that's how the autocorrelation gonna look like. So I'm gonna show you an example of a sessile droplet sitting on a heater. So I'm gonna heat it up from bottom. You see the interface already, and wherever goes white is wherever it turns to solid. So initially everything is Newtonian, and then you start getting a skein of solidified liquid at the surface, and at some point the heat conduction kicks in from bottom. So this confused me for a very long time. So these are the snapshot of the same experiment. That why I heat from bottom, so I'm expecting solidification happens from bottom. But every time I did the experiments, the solidification starts from the skin on the interface. And the reason we found out it's happening that is the air around the droplet. So it's a heat conduction or diffusion in the air that is rather fast. You heat the air, and that's enough to evaporate the tiny bit of liquid at the interface. And even you lose some water at the interface, you locally increase the concentration of your polymer. Therefore, you solidify your polymers there much faster, right? Because if you remember, this transition from liquid to solid was also polymer concentration dependent. But at some point, the heat conduction kicks in, and that's the layer that is a solidification, in the bulk solidification, if you want to name it. Okay. So we use the same method to look at droplets that are slowly spreading on a surface to see when a solidifying, the spreading droplet stops moving. The questions that many of you know, that it's been there for a very, very long time, but now we have a device and a method to look at it in situ inside the droplet by direct observation. So experiments look like this. This is the droplet. You don't see here because that's a needle that is injecting the liquid. There's a video I'm going to show. This is the substrate. It's deformed because because of refraction of the light. So this is not deformed in reality. It's actually a flat surface. And this is the interface of the droplet. I'm going to inject the liquid, and it's going to spread. Right? So this droplet spreads, it stops moving, and at some point you start getting the solidification, which is very much like a sessile droplet. You get the skin first, and you get the bottom first. So I can correct for this curvature, which we did. So here is maybe better snapshots. So we inject the liquid from this nozzle. It starts spreading nicely as a capillary spreading looks like. At some point it stops spreading, and we don't see any signature of solidification. That gives us the hint that what stops the droplet is a very, very small solidification at the contact line, in fact. And that's enough in a low speed spreading for the droplet to stop. What happens later is like a previous experiment I showed you. You get this skin first, and then the bulk conduction kicks in, and the droplet fully solidifies, in fact. Okay, so back to the main question I raised. Can we control the final radius as a function of temperature? So here's a temperature rate. And here our experimental results is again very easy. You increase the rate of heating higher, and you stop the droplet from spreading sooner. So it happened to be an external method, a method of that you can control the final radius externally. In the 3D printers, you can do this, you can control it, but funny enough, this is a reversible process. So if you cool down everything, it turns to liquid, so you can also clean up whatever you print. Okay, and back to the solidification problem between these two schools of thought, that is it the bulk solidification that stops the droplet, or is it the contact line solidification that stops the droplet? We think actually all you need is a microscopic solidification of the contact line that arrests the droplet, which seems to be similar to what recent finding in this lab is too. Okay, you can do the same thing for impacting droplet. Same droplet, it impacts at low temperature and at high temperature, and you can see the final radius is different. So it even works for inertial system. You don't have to do it for a small spread. And you can go ahead and do the analysis as a Reynolds number, which depends on the impact velocity and a non-dimensional temperature, and this map gives you how big your final radius is. Okay. Is it a good time to stop? Or I go ahead. Do I have okay. Then I show you only one thing that I've done when I start working in the lab of Detlef Lose. So one of the things that we struggled quite a lot with all the methods that I showed you, they're all nozzle based. And if you ever use a 3D printers at home in the lab, these nozzles clog quite a lot. And we start thinking, can we have a 3D printing method? Forget about whatever I've done so far. Can we make a 3D printing system that doesn't have nozzles and use another technique? And we basically start moving to systems that are laser based. So systems that look like this. We start shooting lasers to viscoplastic liquids. These are 5 nanosecond laser pulses, which we can control very, very accurately. And then you get, because of bubble cavitations, you start getting these jets that looks like this. This is a very bad jet for 3D printing, but it's beautiful, so I'm going to show you. So the idea is that if you control this jet, I can put a plate here, and I harvest the droplets out of this jet, and using that I can 3D print. And there's no nozzle, so life is much better. If you're curious that how this method works, this is a high-speed video of the bubble deformation in 5 million frames per second. So this is a thin layer of the liquid, and the bubble, you even saw this shock waves that gave us a lot of problem actually in the beginning. But these bubbles grow and collapse, and because of that grow and collapse, you get the free surface jet on the bottom. It's different than the bubble bursting problem to some great extent. Okay, so what we found out in the end is that if you have a low yield stress or high yield stress, you get different shapes. So if you tune the rheology of your materials, you can get the jets that are perfect for 3D printing. And that's actually what we did with our industrial collaborators. We are now able to 3D print circuits in a very, very fast rate by silver paste, which silver paste is actually a viscoplastic material, so if you do a rheology. And you can plot it in a phase map that there is a good regime to do this printing, and that's where this green area is. That's a function of Weber or Reynolds number. These are very complicated, Weber or Reynolds number, because they have optics and laser property in them too. So you have to start from optics, go to hydrodynamics to generate this. But long story short, you can, now we know where to go to print using this method that doesn't have any nozzles in it. Okay, so I conclude maybe at this point. So I told you about viscoplastic spreading, how to get the final shape in different theory computational experiments. And I told you a little bit about thermoresponsive polymers, and this technique that I showed you in the end with the laser is called laser-induced forward transfer, or LIFT for short. And we also work on that and plan to work a little bit further. So where we're going with these experiments right now is that one is the using, we still think using this so-called simple yield stress fluids, where elasticity effects are not significant, has a lot of potential to understand more about fundamental physics and also real application in printing. However, you can extend whatever I said and include the effects of elasticity. So numerically, we are moving towards Elastovisioplastic models when you also add elasticity to the models and see how much that change when you're in the viscoelastic regime. But that being said, we are very much interested in a pure plastocapillarity regime, which is very hard to do it on the ground because there's always gravity. So now with collaboration with German Aerospace Center, we are also doing the similar experiments, but in zero gravity, when we use drop tower, we spread viscoplastic droplets and we look at the final shape, etc. Okay, so I finish by my acknowledgement. Boris Istobel and Neil Bamforth were my PhD advisor, which I did most of this work with them. Thanks so much for listening. I do some shameful advertisement that I have an opening for a PhD positions in my group to work on the computation and theory of similar things, droplets, bubbles, in viscoplastic or elastoviscoplastic fluids. If someone is interested, I'll be more than happy to talk. Thanks so much.
Thank you very much, Mazi. Are there any questions?
First part, when you are studying spreading of your viscoplastic materials, I am wondering why you are so embarrassed with the boundary condition. Where is it because your equations give you these undulations, so you cannot assume that there are no?
Yeah, so the equations give you the undulations immediately. The problem is that if you want to solve y equal to 0 equations, then you have a differential equations that need boundary conditions on the left and right. Left is fine in the center of droplet, but the right one is where these undulations happen. So the question naturally is, so where does these undulations end and what is the derivative?
There and
Exactly, so what's the first derivative, what's the second derivative, what's the third derivative? When you have these undulations that are decaying, you should really know about the detail of their shape, how do they decay, to be able to first find out where they end, so that's final radius in a sense, and when and how the derivatives look like, microscopy. So that's where the difficulties in fact come. Yeah, I hope I answered.
So about these undulations, are they do they happen in real life, or is it just
Excellent question. So in the Newtonian droplets, we start using the method called digital holographic microscopy, DHM, if you know that, which can go to nanometer resolutions, and there we saw it crystal clear. So I mean, not crystal clear. So we get two waves almost, and that when I mentioned about the Newtonian wedge, oh, I have it actually, very much ready for it. So it's a Newtonian droplet spreading, and that's where you get the undulations, and you do it with DHM, which is more complicated than a box only, and that's a droplet invading, so I'm looking at the drop advanced contact line, and these fringes, you can translate them to the height, and if you do that, you get the undulations that look like this. Okay, what we found out, not that we're talking about it, if your capillary number goes above that critical capillary number, you actually lose undulations. So this wasn't clear at all. We thought this experimental error, but happened that it's not. Again, since we're talking about it, you can do the theory and get exactly what that number is, which is on, if I remember, is, oops, sorry. Yeah, it's that blue line is the theory, comes from Stokes equation. Lubrication equation doesn't give you have to do high order solutions to be able to do that. So there's this new singularity that we found out. So you can see undulations. So this is the amplitude of undulations, in fact, for Newtonian case. For the viscoplastic case, we have no experimental proof of that. The reason is that even you can see mathematically, it's not just the amplitude. It's not like a wavelength that drops exponentially in viscoplastic case, but it's also the amplitude. So that means that the moment you introduce a little bit of yield stress, these undulations die really quickly, and so in experimental, so they are there most likely, but they're so small that we can't resolve. Yeah. Which is unfortunate, but we hope we can do it.
Something which is not clear for me is like the influence of the heat when you're doing the spreading of your material and when it does a rest. Because it seems that evaporation plays an important role.
Yes.
So finally, is it like heating or evaporation which plays? Like if you change the humidity, for example, in the room, will it change the spreading diameter?
Yeah.
So finally, evaporation plays a stronger role than heating, or not?
It's a combined thing. So
Yeah.
there are two questions that the curve that, for instance, I showed you about that final radius goes down, the moment of arrest.
Yeah.
So I only showed it as a function of temperature gradient or the heating rate, but you can plot it in a three-dimensional curve, including humidity, for instance. So you can change the thermodynamic of the system and the final radius change, because evaporation has become important, in fact. But about the mechanics or the that arrest the droplet, it seems like that because of evaporation or heating, you get this solidified contact line, and that's the moment that droplet stops spreading.
Yeah.
But you're right. I mean, the evaporation changed the humidity changed the whole dynamic of the system in principle. For when you use thermoplastic.
You could do the same experiment with no heating and just playing with the humidity.
Yes. Yeah, but it takes a lot of time. Yeah.
Okay.
Yeah. It takes much longer if
Okay.
you don't hit it exactly. But you can do that. Yes.
Okay.
Thank you very much. That was very nice. Just a question on, as I'm sure you know, some people argue that pure yield stress fluids don't exist, and
Yes.
there's always elasticity, in particular, close to the yield stress limit.
Yep.
And in some cases, people say that this is the dominant effect in real experiments. So could that be a source of discrepancy in your comparison with, you know?
So I have a slide because which looks like this. So people always ask me, what about elasticity? And that's the elephant in the room. In fact, when you talk about pure viscoplastics fluids, and so one potentially can extend the systems to Elastoviscoplastic model. So there are many of them. Soramitos model that I'm sure you know, familiar, for instance. That's a model we're going to actually implement systematically in basilisk. So this one I got it from the work of Lou and Forte in Marseille. And so the difference here is that now you define this creep term that has elastics effects in it too. When you use these simple fluids, the moment that the fluid, I mean, when I showed this rheology, that there is G prime and G double prime, they really decays rather quickly. That's correct. When they move towards the jamming or stopping, they become significant. So we shouldn't rule out the elastic effect at the moment of spreading at all. But I'm not sure how effective they are. You can do the calculations based on relaxation time and experimental time scales, and that's typically give you a Deborah number that is not significant. But that's very naive to say, because Deborah number is 0.1, therefore it's not important. Could be that it's important. So the honest answer is we don't know. And I think there is a lot of room, and I think it's a very, very important question. So that's the direction we want to go, to repeat the exact same thing with elasticity included, and then see the difference between that.
Well, if there is no extra question, Mazi, thanks again.
Thanks so much.
And yeah, there is time for extra visits.
My pleasure. Thanks so much.